Hi. Last lecture we learned about the sun. We learned about the structure of the sun, we learned how it makes energy, and in this chapter we're going to be learning about other stars. We'll see features of stars that we look at to characterize them and classify them, and we'll see how those different aspects of a star are measured. And we'll be referring back to things that we've learned earlier in the course, like the Doppler effect and Wien's law and the Stefan-Boltzmann law. Then we're going to take that information and compile information on all the different types of stars that we can observe to see if we can notice any trends. This information will be summarized in a very important diagram, the most important diagram in astronomy, called the HR diagram. So we'll learn how that's put together and how to interpret that as well. While there are a number of things that we can measure or observe about stars, remember that everything that we learn about stars comes from a very detailed observation of the light that we receive from them, looking at things like Doppler shift and spectral characteristics and so on. Here are some of the things that we can measure. We can measure the spectrum of a star, that is the rainbow of the star and all of the absorption lines that would correspond to electronic transitions in the elements in the atmosphere of the star. We can observe binary star systems. These are systems where two stars orbit one another, and we can learn a lot of important things by observing those, like the star's mass. We can use parallax to measure the distance to stars. Remember, that works for stars that are relatively close to Earth, but it's still a very useful method. We can also look at the proper motion of stars, that is, the way that the stars actually are moving through space, not the way they appear to move as the Earth moves through space, or not the apparent motion due to parallax, but the way the star is actually moving. We'll learn about something called standard candles. These are astronomical objects whose brightness is well understood, and therefore we can use the observed brightness from Earth to determine how far away the standard candles are. That lets us determine the distant objects that are near those standard candles. We can also measure the apparent brightness of stars, that is, how they seem to us here on Earth, and that would include both the actual brightness of the star and its distance. Of course, the farther a star is from us, the dimmer it will appear to be. Once we've measured or observed these different properties of stars, then we can determine some of the basic properties that correspond to the star. And here are some of the properties that we want to observe. One is the luminosity. Luminosity, we'll talk about all these in a little bit greater detail later, but luminosity is the brightness of the star as observed from a standard. We can also, if we know the luminosity and we know how it appears in our sky, we can determine the distance to the star. From the star's spectrum, we can determine its temperature. We can determine the size of the star and the mass, the composition of the star, again from the spectrum, velocity of the star using the Doppler shift. Usually we can't measure these properties directly. For example, we can't measure the mass of a star directly, so we need to use other measurements like the way binary star systems move, and that can allow us to determine things like the mass. So we'll be using basic laws of physics and observations in order to infer other important properties of stars. In order to do that, we need to understand what are truly the properties of the stars and what are due to observing them from Earth. In other words, due to how far away those stars are from us. And that brings us to the idea of relational versus intrinsic properties. A relational property depends on where we're observing from. In other words, distance, as an example, is a relational property. If we're close to something, then then the distance to it is small. If we're far away, the distance is large. That's really obvious. Velocity depends on how fast the distance is changing. Those depend on where Earth is in relation to the thing we're observing, the star we're observing. There are some other properties that are really just characteristic of the star itself, and it doesn't matter where we are. The star has a certain temperature, it has a certain mass, it has a certain composition, luminosity, and size. So these are the inherent properties of the star, and they're going to be the same no matter where they're observed from. And those are the things that really tell us what the star is about. Let's compare two properties, brightness and luminosity. I already alluded to this difference. These are both important properties. Brightness is something that we can observe directly from Earth, and luminosity is an intrinsic property. It's just how much energy the star produces every second. So the luminosity of a star doesn't depend on where we're observing from. The star is going to produce a certain amount of energy per second, no matter whether we look at it or not. But the brightness is really going to depend on how far away the star is. As an example, if you have a flashlight, it's got a certain amount of light that it produces, and if it's right next to your eyeball, it's going to appear very bright, and if it's at the other end of a soccer field, then it's going to appear kind of dim. So the brightness varies, but the luminosity of that flashlight would be constant. So that's the difference between luminosity, which is intrinsic, and brightness, which is a relative property. Based on this idea of brightness and luminosity, we can define two measures of how a star appears or how it is intrinsically. And we call this the magnitude of the star. We'll use the same word for both those concepts. One is the apparent magnitude, and that is the brightness as it appears. So it's got the word appear in it, as it appears from Earth. So a very bright star that's very, very far away, I should say a very luminous star that's very far away, might look just as bright as a star with low luminosity that's near us. The other type of magnitude is the absolute magnitude, and that is independent of where it's observed from. And what we can do is make a correction to the apparent magnitude and describe the luminosity or the brightness of a star as if it were a particular distance away, and the standard distance that's been selected is 10 parsecs. So let's look through the slide. Apparent magnitude is one way to measure, and that depends on distance, which I've just said. The absolute magnitude is how bright it would seem from a distance of 10 parsecs. And we can calculate that because we know that the apparent brightness varies according to an inverse square relationship. That means if we know how it appears and we know how far it is, then we can actually calculate how it would look from a distance of 10 parsecs. So if we put everything into terms of absolute magnitude, then we can compare stars on an equal footing. We take out the effect of the differing distances to stars. So we've been using this term magnitude, and magnitude in astronomy refers to the brightness of the star, whether it's apparent or absolute. And this scale originated with the ancient Greeks, including Hipparchus and Ptolemy. And of course, we've heard Ptolemy before when we talked about the Ptolemaic model of the solar system. And they grouped stars into 6 groups according to how bright they are. So the brightest stars were given a magnitude of 1. The ones that were a little less bright were 2, and so on. And the very dimmest stars that could be seen were magnitude 6. So their scale was fairly narrow, 1 through 6. As time went on, we took this ranking system and made it more quantitative, and now we can have negative magnitudes, and we can have magnitudes greater than 6 because we can use telescopes to observe stars that we can't see with the naked eye. So on this scale, it's a little bit counterintuitive. The more negative a number is, the brighter the star is, either as it appears in the sky or on an absolute basis. Positive numbers are dimmer. So it's kind of like a golf score where a low number is stronger or better than a high number. In our scale, every step that you move lower in magnitude corresponds to a factor of 2.5 times brighter. So that means a magnitude 3 star is 2.5 times brighter than a magnitude 4 star. A magnitude 2 star is 2.5 times 2.5, or 6.25 times brighter than a magnitude 4 star. On this scale, the sun has an apparent magnitude of negative 27. So obviously very, very bright in our sky. And using this scale, the apparent magnitude of the faintest stars that we can observe with Hubble is positive 32. So these are, if we could see these stars with our naked eye, they would have this very, very high number, which means they're extremely dim. Over here you can see the scale, and you can see that with binoculars you can get up to 10. Remember, the naked eye limit was a magnitude of 6. The North Star, Polaris, is 2.5. Venus, which is the brightest object in the night sky after the moon, when it's brightest, it's at negative 4.4. And then here you can see anything beyond 10 is going to be hard to observe. You'll need a telescope. For large astronomical telescopes, you can get out to a magnitude of 27. And as we said, with Hubble, we can get to 32. I didn't update the slide for the James Webb, so I'm not sure what that number is. So now let's look at the relationship between the brightness, or the apparent magnitude, and the distance. The light from a star spreads out as it moves away. The light comes in from a star, it spreads out in a spherical way. So the same amount of light is spread out as you move away from the star over spheres of different areas. So when we're close to the star here, well, we've got distance equal 1. All that light is passing through this sphere. We move to distance equal 2. That same amount of light is now spread out over a much larger sphere. And at this distance here, 3 times, the light is spread out over an even larger sphere. That means the light that falls on a particular detector, whether it's your eyeball or a telescope, is a smaller and smaller fraction of the total light that's emitted by the star. And because the size of the sphere, the area of the sphere, increases with the square of the distance, or the radius, we call this an inverse square law. The light is spread out over a larger and larger sphere. So the brightness, this is shown in an equation, the brightness is going to be equal to the intrinsic luminosity of the star divided by the area of the sphere that would have the distance d from the star. So if Earth is d light years from the star, then the area of the sphere that would include the Earth would be 4 pi d squared. If we have a star that's twice as far away, in other words, if we replace d with 2d, then this will be 1/4 the brightness. The 2d would become 4 when we square it. So inverse square law. We've seen this before and we've talked about it before. This same sort of thing appeared in the Stefan-Boltzmann law from before. We have to observe the luminosity, and we can observe the temperature based on the spectrum of the star, and from that we can calculate R. We can use the Stefan-Boltzmann law then to determine the size of the star. If we know the luminosity, which we measure by how bright the star is and how far away it is, and we know the temperature, then we can determine the size of the star. This is the only way to do it for most stars. For very few stars, we can actually observe the diameter of the star. But most stars are so far away that they only appear to be pinpoints of light. We can't actually see how wide they are. We can see how wide the sun is. That's close enough. We can that covers a half a degree in our sky. We can see how big Betelgeuse is here in the constellation Orion. Here's Orion's belt, 3 stars, and his shoulder is Betelgeuse. It's a reddish star. And because it's a giant star, a red giant star, and it's close enough, we can actually measure the diameter of Betelgeuse. But most stars, we'd like to know how big they are, but we can't measure them because they're so far away. So we can use the Stefan-Boltzmann law along with the distance to the star to determine the radius or the diameter of the star. Recall from before that the way we determine the temperature of a star was by looking at its spectrum and by finding the lambda max, which is the peak wavelength, and using Wien's law. So here's Wien's law to remind you. And we measure lambda max. Here's lambda on the x-axis. And we find whatever the peak is for the curve. And we can plug that into this equation, rearrange it, and solve for temperature. And here you can see the temperature here is 5,500 kelvins. Down here, this last curve with the longer wavelength, lambda max, is 3,500 kelvins. So that's how we can determine the temperature, which is important on its own, and with the use of the Stefan-Boltzmann law, as we saw in the previous slide, allows us to determine the diameter of the star. If we want to determine the chemical composition, what elements are present in the star, then we can use the absorption spectrum. And I've shown a little absorption spectrum here to remind you what that is. So we have a rainbow from the star, a continuous spectrum with some missing lines. And those missing lines are a fingerprint for the element that is absorbing that light. This happens to be the absorption spectrum for hydrogen. So we can determine what elements are present, and depending on how strong these absorptions are, how much dimmer the light is at this wavelength, that tells us how much hydrogen or helium or iron or whatever element it is present in that star. Other properties that we can measure: the mass and the velocity of a star. We can't weigh a star. We don't have a scale. We can't get to them anyway, but we can look at the width of those absorption lines, the spectral absorption lines that we just saw in the previous slide. And if those lines are wider, then we can infer that the star is more massive. That's because if the lines are wider, that means that there's more thermal energy, it's hotter, and there's more pressure, and that would only happen if the star were more massive, had a greater gravitational pull. And so by looking at the line width, we can measure the mass of a star. We can also determine if the star is approaching us or receding from us by looking at the Doppler shift of those absorption lines. And this is illustrated on the next slide. Here we see 4 graphs, and on each of these graphs we see a representation of the width of the absorption line. So remember that rainbow that had the black bars in it. This is one black bar from that line, and it's not a perfect rectangle. It starts out with very little absorption and then reaches a maximum absorption right in the middle of that black line on the previous slide with the rainbow, and then it drops off. So we're actually looking at how wide this line is, and we're looking at where the center of this line is to determine these important features of the star. This first graph shows an unshifted absorption line. So there's no Doppler shift for this line, and this would occur if the star is not moving towards or away from the Earth, or if it's moving kind of across, or if it's stationary. So this is unshifted. That's the same wavelength that we would observe for this element. Let's say it's carbon or iron or something. It's going to come out at this wavelength in the laboratory, and because it's at the same wavelength in this spectrum, we say, okay, that star is not moving towards or away from the Earth. In spectrum B, we see that the absorption line is shifted to a longer wavelength. We call that a red shift, and that occurs when the star is moving away from the observer, away from the Earth. So that's a red shift. Here we've got a blue shift. The star is moving towards the Earth, and so the wavelength becomes shorter, and the distance that the wavelength moves shorter, in other words, the further it moves towards the blue, that means that the star is moving towards us faster. Finally, in D, we see a really broad or fat absorption line compared to the other three. In this case, we're looking at the effect of motion away from the Earth and towards the Earth. Here, the motion is we're looking at the individual atoms in the star. It's the superposition or the combination of atoms that are moving far away or moving away and atoms that are moving toward. And if the star is very, very hot and dense, then it's going to have a greater spread in the wavelengths or a wider line. And so that spread is what lets us determine the temperature and the density of the star. Another way that we can determine the mass of stars is by looking at binary star systems, which I mentioned in the introduction to this lecture. Binary systems are systems of two stars, and those stars are orbiting their common center of mass. Sometimes we say they're orbiting each other. And we can look at the rate at which they orbit. We can look at their pace of orbit and the distance from the center of mass, and use that to determine the mass of the two stars in the binary system. There are a number of different ways that we can observe binary star systems. There are astrometric and visual binaries, spectroscopic binaries, and eclipsing binaries, and we'll see each of those over the next couple of slides. If the binary system isn't too far from Earth, then we can see the motion directly, and the stars seem to wobble a bit as they orbit one another. If we can see both of the stars, if they're both bright enough to see, then we call that a visual binary. If we only can see one of them and the other one is too dim to see, either too weak or too cold, then we just see a wobble in the orbit of the one that we can see. In order to do this, of course, we need to have a telescope that can resolve the two stars. Remember that resolution is the ability to distinguish objects as separate and distinct. Another way to observe binaries is spectroscopically. In this case, we're going to be using the Doppler shift. As the stars are orbiting their common center of mass, the light from one star will be red shifted and the light from the other star will be blue shifted, and then it'll switch. And so here in this top example, this smaller star is moving away from the Earth as it moves around here, and the larger, brighter, whiter star is moving towards us. So this star will be blue shifted and this one will be red shifted, or as the orbit progresses, they will switch, and so we'll move from a blue shift to unshifted to a red shift. So that's a spectroscopic binary. And this is similar to what we saw before when we were talking about exoplanets. It's similar to that radial velocity method for detecting exoplanets, where we can't see the planet, but we can see the effect on the star itself. Finally, we have eclipsing binaries, and this occurs when the plane of the star's orbits about one another is seen edge on from the Earth. So one of the stars will pass in front of the other star. And even though both stars are producing light, when one is in front of the other, there's going to be a dip in the amount of light that comes out. And so we can see the effect of one star passing in front of the other. And so this is, again, going to let us detect the binary, and we can measure the period and so on and determine the mass of the stars in that binary system. And this is sort of like that transit method that we looked at before when we talked about exoplanets. Another property that we're interested in is the velocity of stars, or their proper motion. That is how the star is actually moving through space. Again, this is distinct from parallax, where over the course of a year we observe the star from different angles and it appears to move against the background of stars. Here, the star is actually moving across the background of stars. And so from one year to the next, the star will appear to have shifted because it actually has shifted. So we can determine that sideways or lateral velocity. What are some other things that we can measure about stars? We can measure the distance of the star. Remember, we talked about parallax. That's observing the star at different times in the year. We look at the nearby star against the background of stars and determine the angle through which it shifts, and we can use trigonometry to determine the distance of the star from the Earth. This only works when the stars are relatively close, because this angle, this parallax angle, gets smaller the farther the star is from Earth. So even the closest star after the Sun to Earth has a parallax angle of less than 1 arcsecond, or less than 1/3600th of a degree. Anything further is going to have an even smaller angle. So before long, you're past our ability to detect the amount of parallax. So we can measure out to about 9,000 parsecs, but even that's an amazingly precise measurement, but that's only 20% of the width of the Milky Way. Another way to measure distance is to use something called standard candles. And here, a standard candle is something whose luminosity we can determine by some other method. And we'll look at Cepheid variable stars in a moment to see how we can use that to eventually determine the distance to a star. So if we know the luminosity, that is the intrinsic brightness of a star, and we know how bright it appears from Earth, then we can determine how far it really is. We can do a calculation using that inverse square law. And with the Cepheid variable stars, we can determine, well, first of all, these are stars whose brightness or luminosity varies in a very periodic way, and the length of time, or the period over which that variation occurs, tells us about the luminosity of the star. So by measuring the period, we can figure out the luminosity, and then we can compare that with how bright the star appears to be. Let's see that on the next slide. So here we can see a graph of the brightness of a Cepheid variable star, and it's changing in a very regular way. You can see the actual data points, or you can see the curve drawn through them. And this happens for this particular Cepheid variable star. It happens over a period of about a month, or 31 days. And by measurements of lots of these stars and using other information, we can determine the relationship between the luminosity of the star and the period of the variation, the pulsation. And you can see this graph here. It's a very nice relationship, very predictable. And so if we know the period, then we can come up here and read the luminosity. So this star we're looking at in the top graph, its period is 31 days. We'll come here, go up to the graph, and we say, okay, that star has, I'm going to say, about 20,000 times the sun's luminosity. Of course, if you're doing this for real, you'll use an equation and measure it off the graph. All right, so if we know the luminosity and we know how bright the star appears, then we can calculate the distance. So once we know the distance of the star, then if there are other objects that are near that Cepheid variable, we know that they're the same distance away. So this is a really useful way to determine the distance to a star that's too far away to use parallax. As we proceed through the course, you'll see some other ways to determine distance. And this is a really important feature to know. We need to know how far away something is so we can determine how bright it really is. There are some Cepheid variable stars that are so bright that they can be seen in other galaxies. So thousands or millions of light years away, we can observe individual Cepheid variable stars, and we can determine their distance, and therefore we know the distance to the galaxy and the distance to the other stars that are in that galaxy. So what we've seen so far are lots of different important properties of stars. Now we're going to take these different properties and start to put them together and correlate and see what we can understand about different types and classes of stars. I've told you before that the sun is about 4.5 billion years old and that it has about another 5 billion years left in its life. How do we know that? No one's been able to observe any star for even 100 years. So how can we possibly know about things that are going to last for millions or even billions of years? That's the subject of the next section. Compared to the human life cycle, or even the life cycle of our entire civilization, stars live too long for us to follow any individual star. Stars live for millions to billions of years. In order for us to understand how stars live and evolve and eventually die, we need to make observations of many, many, many stars at different points in their life cycle and piece everything together. We're going to observe stars of different size, of different temperature, and of different age, and put this all together into a map that will help us understand how all stars form, evolve, and eventually die. When we do this, then we'll understand more about the sun and about all the stars in our galaxy. One of the first things that scientists do in any discipline is make observations and start to look for commonalities or classifications. For stars, we have something called spectral classification, classification by the spectrum of the star, and this is basically the classification according to the temperature of the star. Not exactly, but that's close enough for us. And so stars are grouped into different spectral types, and the spectral types are O, B, A, F, G, K, M. And this is kind of weird, but it's really a historical artifact. Originally, as these stars were being classified, they were just labeled A, B, C, D, E, and so on, just kind of typically the way you might do it. But as understanding improved, some of those different groupings of stars were combined together, and they kept the original letters and reordered them, and now we end up with this ordering O, B, A, F, G, K, M. And one of the astronomers who first put together this spectral classification came up with her own, her name is Annie Jump Cannon. She came up with her own mnemonic to remember the order of these letters, and her mnemonic was oh, be a fine girl, kiss me. You could make, oh, be a fine guy, kiss me, or whatever you prefer, but OBAFGKM. O is the hottest type of star. Typical surface temperature of such a star, 42,000 degrees. M is the coolest, and its surface temperature is around 3,000 degrees. The Sun is a type G star, and its surface temperature is 5,800 kelvins, so you see it's right in the range of this 5,560 kelvins. So this is one feature that we can graph, the spectral type or the temperature, and we're going to put that onto a graph along with the luminosity on the next slide. The figure you're looking at, and that we'll be studying in some detail over the next couple of lectures, is called the HR diagram. HR stands for Hertzsprung-Russell. Those are the two scientists who developed this independently. It's named after both of them. What's plotted on the y-axis, the vertical axis, is the luminosity of the star. Remember, that's the intrinsic brightness. And that is measured in solar units. So 1, anything with a luminosity of 1, has the same luminosity as our sun. And you can see it's a logarithmic scale. So each step here on this graph is 100 times more luminous than the step before. 1, 10 to the 2, that's 100. 10 to the 4, that's 10,000. 10 to the 6, that's 1,000,000. And here, I don't know why we've gone to 10 to the 7th instead of 10 to the 8th here. I'm not sure if that's a mistake. On the horizontal axis, on the x-axis, we have the temperature of the star or the spectral class. So we can see down below here the spectral class, OBAFGKM, or the temperature that corresponds to it. Notice that the high temperature is on the left and the low temperature is on the right. That's the way it's always graphed. So that means that the very, very luminous hot stars are in the upper left-hand corner, and the very cool and not very luminous stars are down here in the lower right. If we know the luminosity, which we can read off the vertical axis, and the temperature, which we can read off of the horizontal axis, then we can determine the size of the star, or its radius, using that Stefan-Boltzmann law from before. And so we've got these lines here. Everything along this line is 10 times the size of the sun. Everything along this line is the size of the sun. So as we cross here, this is the size of the sun, and right here's the luminosity of the sun, because it matches up with 1 here. So the sun is going to be right there on this blue line somewhere. And as we move down, these are getting smaller and smaller. So these tiny stars down here, we call them dwarfs. They're much smaller than the sun. So we can see that there are kind of 3 main groups here. There's this group here, and we've drawn a little kind of a shaded line through those. We got a group of stars in the upper right-hand corner, and we have some down here below. And we're going to call these the main sequence, the giants, and the dwarfs. So the giants have high luminosity and low temperature, upper right. Remember, to the right is low temperature, up is high luminosity. The main sequence, we're going to spend a lot of time talking about the main sequence. Those are stars that are going through hydrogen in their core. We'll talk more about that later. But this is kind of a band from the upper left, which is high luminosity and high temperature, to the lower right, low luminosity and lower temperature. And then finally, we have the dwarfs, which are to the lower part of the graph. That means they have low luminosity, but they're off to the left, so they're high temperature. And one way to remember that is, I guess, a little joke. Question is, what did the college students say about their date? They went out on a blind date, and they said, "Oh yeah, my date was kind of a white dwarf." Well, what do you mean by that? Well, a white dwarf is really, really hot, but not too bright. So, high temperature. Oops, sorry. High temperature and low luminosity. So if we look at the HR diagram, that doesn't show how stars evolve. They don't move along the main sequence, for example. It just shows us a snapshot of the characteristics of the stars in the sky right now. Stars, through their lifetime, do occupy different places on the HR diagram, and we'll be discussing that in future lectures. When the stars start their evolution, they start out on the main sequence, and they spend time there, but after they've consumed the hydrogen in their core, then they're going to leave the main sequence and move through an evolutionary path that we'll be discussing. So stars spend most of their life cycle on the main sequence. That's where we see most of the stars, on that diagonal line. So the sun is on the diagonal line on the main sequence. It's a main sequence star. And if we look back at the sizes, I'm not sure if I can scroll back since I'm recording. Nope, I can't. It won't let me. But the main sequence stars are all in a similar size range to the sun. Within one order of magnitude, that means either 10 times bigger than the sun or 10 times smaller, 1/10 the size of the sun. And remember, we talked about hydrostatic equilibrium last lecture. That is the balance between gravity trying to collapse or crush the star and the internal pressure from the fusion keeping it inflated or puffed up. Main sequence stars are maintaining their equilibrium through fusion of hydrogen in the core. And that's what they spend most of their time doing. Once they're done burning through the hydrogen, the rest of their life cycle proceeds pretty quickly. As you can see, the main sequence covers a very broad range of luminosities, from 1,000,000 times the luminosity of the sun down to about 1% the luminosity of the sun. So a very broad range of luminosity and a very broad range of temperature, from say 30,000 kelvins all the way down to 3,000. So a broad range of temperature as well. And that's not because they have different ages. Old stars aren't really weak and young stars aren't really bright, but it's because of the mass of the star. The mass is the single most important determinant of the life cycle of a star, where it enters the main sequence, how long it stays there, and what happens to it at the end. And as we'll learn when we study formation of stars, the mass is set when the star is first starting to form from whatever cloud of gas and dust is out there in space. It starts to collect and coalesce. If it's a huge amount of gas and dust, then you're going to end up with a big star. And if it's in a place where there's not as much gas and dust, you'll have a smaller star. So that's what's going to determine the mass. And the mass is going to determine where the star starts on the main sequence, how long it stays there, and what happens to it afterwards. And perhaps surprisingly, perhaps backwards from what you might think, the bigger the star, the shorter it lives. The more massive, the shorter the star's lifespan. Why is that? Well, a more massive star has much, much stronger gravity, and so that pushes everything in the core together much more densely. If the atoms are crowded in the core of the star, then it's going to be hotter, and there's going to be greater fusion, greater opportunity for hydrogen nuclei to encounter one another. They're going to slam into each other faster, and they're more likely to fuse. And so the rate of fusion will be very rapid. If the rate of fusion is very rapid, then they're going to burn hot, and they're going to be really bright, but they're going to use up their hydrogen faster than a star that's just poking along. And then once they use up all the hydrogen in their core, then they're finished on the main sequence, and they're going to continue their evolution. And as I've said, they're going to either have a supernova, turn into a neutron star or a black hole or something like that. More on that in a future lecture. So if we want to look at the amount of time that a star spends on the main sequence, we have to look at the mass of the star. This slide shows the mathematical relationship between the time that a star spends on the main sequence, TMS, main sequence, and the mass of the star when compared with the mass of the sun. So we see that, first of all, we're going to start with 10 to the 10th years. That's 10 billion years. So if the star is equal to the mass of the sun, then we'll have something that's m over m sun is going to be 1. And so 1 to the negative 2.5 is still 1. The lifetime on the main sequence will be 10 billion years. If the star is more massive than the sun, then this number will be greater than 1, and we're raising it to a negative power. That's like a reciprocal. And so we're going to end up with something that is smaller than 1. When we take this number greater than 1, raise it to the negative 2.5 power, we'll end up with something smaller than 1, which means the lifetime on the main sequence will be less than 10 billion years. So if we now look at this table, you can see that if the star has the same mass as the sun, right here, 1 solar mass, its lifetime on the main sequence will be 10 billion years. If it's twice as massive as the sun, it's only going to be on the main sequence for 2 billion years. If it's 4 times the mass of the sun, now we're down to a few 100 million years. A star that's 100 times the mass of the sun is going to be on the main sequence only for 100,000 years. The sun's going to be on for 10 billion years. And if we look at the other direction, something that's only 8% the mass of the sun is going to be on the main sequence, according to our model, for 5.5 trillion years. Well, our current universe is only 13.8 billion years old. So a star with this small mass would be expected to just keep poking along for many, many times the age of the universe. So what happens then after a star leaves the main sequence? Well, when the star forms, it becomes a star through a process that, again, we'll be discussing in future lectures, but it's going to settle down on the main sequence. And it enters the main sequence when it achieves equilibrium, which is to say that it's poking along at a steady rate. Prior to that, it's just started and it's settling itself down. Once it gets on the main sequence, it's going to poke along here for however many years, depending on its mass, 10 billion in the case of the sun. Then it's going to burn through all the hydrogen in its core, and then it's finally going to move off the main sequence and go through the rest of its evolution, depending on its mass. The star is not going to enter the main sequence and then move along the main sequence, either up or down. Where it enters the main sequence is determined by the mass, and then it's going to leave the main sequence when it's done burning hydrogen and continue with its evolution. So up here, this white star is more massive than the sun. It enters the main sequence at a higher luminosity and a higher temperature. how do we determine all these things about stars and the main sequence and their evolution? We can look at groups of stars that all formed at about the same time from the same materials. These are called globular clusters of stars. So if we think out in space, it's so vast, it's hard to think about how large space is. But in this vast volume of space, there's a lot of gas and dust, and something happens to start that dust to clump up. And as it does, it's going to form a whole bunch of stars, perhaps hundreds of thousands of stars, all forming at about the same time. But there are going to be a whole variety of different types of stars forming, large stars and small stars. And these stars are, as I say, they're all forming at the same time from basically the same stuff, and they're all about the same distance from Earth. So we can really look at them and compare them with one another, with other things being held constant. Their age is constant, their distance is constant. So now we can look at this group of stars and say, oh, we're looking at all the different masses of stars. So when we put all the stars in a cluster onto the HR diagram, we see that stars follow the main sequence, and at some point, at some luminosity and temperature, stars turn off from the main sequence. There aren't any stars up here on the main sequence. There were at some point, but now they've left the main sequence and moved on with their evolution. So the luminosity, the point at which they turn off, tells us that any star older than this has now left the main sequence, and younger stars are still, or smaller stars, I should say, they're all the same age. Smaller stars are still on the main sequence. So that tells us how old this cluster is. So now we know we're looking at a bunch of stars that are, say, 2 billion years old, and we see where they turn off from the main sequence, and we see, okay, these massive stars undergo this kind of evolution, and these smaller stars are still chugging along on the main sequence. By observing lots and lots of star clusters and plotting their stars on the HR diagram, we can start to build a picture of what's going on. Okay, so as I said, the turn-off mass tells us how old the cluster is. We can look at clusters of different ages, and then we can see what happens to stars when they're different ages, how do they evolve, and then we can put all the physics we know into a model and see if we come up with something that kind of matches what we observe from actual star lifetimes. So we're going to go into a lot of this in future lectures about how stars form and the different stages of their life cycle. So this is really an introduction. The HR diagram is a very important summary of what's going on, and we're going to make many references to it. So spend some time figuring that out. Rewatch the lecture, read carefully in the book. It's really important for you to understand the HR diagram. So just to close out this lecture then, we've got a lot of different properties that we can measure from stars, that we can calculate. Again, all of it's coming from a measurement of the light of the star, looking at the wavelengths and Doppler shifts and luminosity and everything else, and that's going to tell us a lot about the star. We understand a lot about what's going on the main sequence. That's when stars are burning hydrogen in their core, and stars spend most of their lives on the main sequence. And the next thing that we want to understand is how stars form, how they get going, how they settle down onto the main sequence, and then what happens when they leave the main sequence. Why do they, and what happens afterward? All right, thank you very much. Be sure to do your reading and do the in-class activity and turn that in before midnight tonight. And I will see you on Monday. Thank you.